Hey folks, welcome to ICCRG. We'll give it a couple of minutes, maybe 5 or so, because this is right after lunch. Okay, folks, it is 5 past. Let's get started. Welcome to the Internet Congestion Control Research Group. My name is Reese, and I'm joined by my co-chair, Vidi, who's remote. And yeah, let's get this session started. Vidi, do you want to kick us off?
Sure. Thank you. Thank you, Reese. Hello, everyone. I am remote today, so bear with me. Note well, intellectual property. I suppose you guys have seen this, but this is important. And we have our audio and video recordings. This is routine, but just so that you know, for new participants, privacy and code of conduct and goals of IRTF. So IRTF is for conducting research. We do publish RFCs, but it's not for standards. But we do encourage research work to come here. Coming to the main items for the work group, we have 2 documents in the work group right now. LEDBAT++ was in a limbo for a bit, but now we are making progress and we are almost there. The IRSG review is complete, and soon you will see that it's published and we will have a number for it. So that's good. If you haven't still looked at LEDBAT++, I do recommend you take a look at it because it is definitely solves the problem that LEDBAT, the original LEDBAT, suffers from. So that would be a good change if you already implement LEDBAT, or if you don't implement LEDBAT, then also it would be a good start. And then we are also going to talk about pacing in transport protocols. And this draft is fast moving. It has been adopted by ICCRG, and we're going to try to finish this draft soon with the open issues that we have, and probably take it to last call in a few months. So if you haven't read it, please do read it. It covers a great amount of information and platforms. And it would be good to get feedback from folks on this draft. And that brings me to the last slide, today's agenda. So we do need a note taker. We have a note taker, right?
I'm not aware of a note taker yet. Who's willing to take notes today? Please. Stuart, thank you so much. Anybody willing to be backup for Stuart? Oh, I see, Greg. Thank you.
Thank you, guys. And for presentation, apart from the share slides, we're going to talk about pacing and transport protocol. Michael is going to present that on site. Say hello to Michael. Then we have congestion notification for multi-resource allocation control. And Mario is going to present that, and that's also on site. And then the last thing that we're going to spend time on is L4S and Prague congestion control. And Kuhn is going to present that on site. With that, we can get started.
Wonderful. We will have Michael up first. Let's get your slides up.
Okay, thank you. I probably have to be in the pink part. Okay, thanks. Yeah, just a quick update about the draft. Primarily, as Vidi said, we're asking for feedback. We want people to take a look at it. We're moving towards the last steps with this, I believe. A couple of things that we added, not much really. Somebody suggested that I should talk about a different Linux kernel version because I want to be able to cite the long-term stable version number here, not some branch. And so double checked, and that code is still valid, and that's still the same in that version. That's an update. Another update is that now there is much more FreeBSD text from Michael Dixon about the rack stack specifically. This talks about socket options that are available with some explanation on what they do. You can enable, disable pacing, configure a burst size, configure a pace rate, and do this separately for slow start, congestion avoidance, and recovery. And as an example in the text from using packet drill with a 1.5 megabit per second rate and a burst size of 4 transmitting the initial window, and it shows a simple case of pacing doing its thing. Then there was a bit of updating in the general considerations. There is one thing in particular I've always wanted to do about this draft and I never got around to do. There is an old paper that a lot of people know about and people have mentioned to me at some point. That's called Understanding the Performance of TCP Pacing. And I knew that there was some issues with it, but I never got around to digging into it, and now I did. So this is a paper that shows some downsides of pacing, but it does so using simulations only. It does so using a pacing rate calculation of the congestion window over the RTT with no additional factor. So that is also something that I think nobody does. And using Reno. Now, problems that they find are attributed to synchronization of multiple connections. It's an interesting paper to look at, but I think much in this paper is misleading and just not really right today anymore. To some degree, an artifact of pacing with a too low rate. To some degree, well, misleading, as in this example here. This is one of the problems that this paper shows, where they say that this looks to me, to them, to be something due to synchronization, which I claim is wrong. If you look at this, the buffer size here is only 312 packets as opposed to the BDP, which is much larger. And there is an issue that I presented in Vancouver. If you care to know more about that, maybe go back to the Vancouver IETF slides. It's also referenced in the draft, and the draft talks about this. The issue is that the backoff after slow start. So there are essentially, in even the very simple case of only one TCP over one bottleneck, no other traffic, there are essentially two reasons for why packet loss could happen. One is that simply a burst is too big and it arrives at the queue that cannot handle it. And the other one is that you exceed the capacity limit. Now, obviously, with pacing, it's more likely that you get the second type of packet loss, which means that you go on and slow start longer, and that's a good thing. That's what we want. But it turns out that when you actually have the second type of loss, when you have the right-hand case, then backing off with a factor of 0.5 is in fact too large. The factor is too large, and you will experience a double drop. So this is a mistake in very basic original TCP. If you don't believe me, go to the slides or talk to me afterwards. I have proof, I have the maths, and it's all tested against Linux, and this is very real. So I believe this is exactly what happens here in this picture, where you see that the more bursty, non-paced traffic is able to back off kind of okay, whereas when you do pace, you get the double back off. So this is a negative side effect from pacing, but it's not pacing being bad, it's the back off not being right for when you do saturate the network. This text has been in the draft before, but this part here motivated me to also add an example to the draft to make this even clearer. So that's in there. Next steps. Well, somebody said that the FreeBSD text could be elaborated a little bit to make the example a little bit clearer, and the macOS description is a bit short, and VD has at some point promised to deliver more, but didn't get around to doing it yet. So that is a plan. And that's all that we authors still have on our to-do list. So I think if you have the time to take a look, then that would be great. Tell us about it, file an issue. That's all I have to say. Questions, comments, anything?
Any thoughts? more implementations. I think I saw a section on quick BBR implementations. Are there any other implementations that might be relevant to?
No. If you have one, bring it up.
It is relevant in a lot of aspects. I think Ingemar did tell us about the real-time thingies, and I don't know if we covered that in the draft, right? For real-time traffic?
Yes, there was. He suggested a bit of text for Scream version 2, and that is addressed. There's a paragraph talking about how Scream does it.
Sounds good. I probably missed reading that.
Yeah.
And then we have Gory, not in the queue, but at the microphone.
In the queue now.
In the queue now, thanks.
Gory, yeah, thanks, Michael. I will read it carefully and send some comments. Probably I could add a little bit about my experience with Quick and the UDP-based interface, which is pretty similar to what you say. So I think the same wisdom applies, maybe a few extra details there.
Yeah, happy to get inputs and suggestions. Okay.
Okay, well, the GitHub is out there, linked from the slides. And please file issues and PRs.
Thank you.
Thank you, Michael. Thank you for bringing this draft. So next up, we have Mario. Hang on,
So, can I start? Good. So, hello everyone. I am Mario Patetta, PhD candidate at CNAM Paris. This is my first IETF. I'm having a great time. So, I'm a little bit nervous as well. So, in this presentation, I will talk about a congestion notification protocol to tackle multi-resource bottlenecks. So I will start by introducing a little bit the context we were working on when we had this idea of multi-resource congestion. And then I will present the multi-resource explicit congestion notification to tackle it. So I think there is a little bit of lag, maybe. Yeah. So let's start. The context is 5G network slicing, but we will see later that actually it can be applied to other contexts as well. But let's start by taking into consideration the idea of having several connected devices that access some services using a shared physical infrastructure. And this physical infrastructure is actually composed of multiple segments. Each segment is characterized by different resources. For example, could be radio spectrum, network resources, bandwidth, computing power, so on and so forth. And in general, these resources are managed by different operators, which need to collaborate to allocate tailored resources for each service. So basically, this constitutes a multi-resource, multi-operator allocation problem, which led to opened the way to the institution of, or it created its own body of literature, which in turn leads to the establishment of a dynamic, hierarchical, and multi-resource scheduling frameworks, where different resource controllers collaborate to assign or to actually translate slice or service level resource requirements into low-level data plane allocations. Then the question that we asked ourselves is, what happens if there is a sudden, unexpected event that causes the resource availability to decrease. For example, could be a device failure or something less disruptive that could be, for example, radio link degradation or maybe a high priority critical mission critical traffic increasing suddenly, causing other services to be starvated. But anyway, what happens if resource availability for a given slice suddenly diminishes? Then in this framework, we have actually we should, since the availability changes, then also the optimal resource allocation should change as well. But in order for that to change, in practice, there will be some horizontal delays due to interoperator negotiations and some vertical delays due to the control plane hierarchy. So the idea that we have is can we somehow bypass this hierarchy, this framework, and use something similar to ECN to deliver this sort of notification directly to data plane equipment by injecting it into affected packets. So this is how we thought of these multi-resource explicit congestion notification. But let's start by defining multi-resource congestion and cross-resource waste. So we say that a resource J allocated to slice I is congested, and the congestion is defined as the amount of resource that we lost for that slice normalized by the original allocation. Then we observe that if there is a congestion on some resource, then the other resources allocated by other resource controllers to the same slice will be bottlenecked because of that. And assuming a proportional dependency between resources, we define waste as the cumulative sum of the cumulative sum over time of the difference between the allocation adjustment that we apply and the loss that has occurred, of course, normalized by the original allocation. So with this definition, if we perform no adjustments, then the waste becomes the cumulative sum of congestion. Whereas if the adjustment is exactly the same as the loss, again, this is assuming proportional dependency, then waste is minimized. So just to give you a visual example, actually there was supposed to be an animation here, but
Are you happy to take questions now, or do you want to wait until
as you prefer. You can go ahead.
I'm Stuart Sheriff from Apple. I'll try to make this quick. On your previous slide, you were defining congestion, and I think that's important. That word is widely used in our industry. Like, to me, congestion is the desirable state of the network. It means you're using it. It's not idle. It's either idle or congested, but you're defining congestion as, you said, the amount of a resource that's lost. What does it mean to lose a resource?
Like this is, I would say, another layer. Like this is multi-resource congestion. Maybe actually in our team we struggled a little bit. Maybe congestion might not be the correct word. We ended up leaving it that way, but I'm very open for feedbacks, and actually I really truly understand it. In our definition of multi-resource congestion is, as I said, if we go back here to this multi-resource orchestration framework, if several resource controllers agree on allocating some resources to a certain service, and one of these controllers or one of these segments is not capable anymore to provide the exact resource that was agreed upon, then we define that as congestion. Maybe congestion is not the right word. Yeah, I can see that.
We could debate separately what the right word is. I wanted to understand. So I think I understand now. You're defining it in your equation of loss over allocation. It's when you've overcommitted something and then you can't deliver what you promised.
Yeah.
Okay. Thank you.
No, thank you for raising that point. Again, there was supposed to be an animation here. I will try to help you visualize it just by my words. So let's suppose that at some point slice I is allocated some amount of resources R1, R2, and R3, and that despite the original allocation, R1 incurs in a 25% resource loss for a period of time that we arbitrarily divide in 10 time slots. Then let's also suppose that assuming a proportional dependency between these three resources, it turns out that R2 and R3 have 25% of their resources that are allocated but not usable because of the bottleneck on R1. So actually those resources are wasted, effectively wasted. And then let's also assume that after 3 time slots, R2 is capable of adjusting. Actually, the controller of R2 is capable of adjusting it to match the loss, the congestion, whereas R3, after 4 time slots, it's also adjusted, but it doesn't match exactly. So there still will be some loss over time, some waste over time. So the waste is actually computed by cumulating the loss, the waste in each. The total waste is computed cumulating the waste in each time slot. I'm very sorry because the visual example is not helping me at all. But anyway, the idea is behind this MRECN is to make so that congested devices, so devices whose capability worsened, or if the congested device failed, the redundant backup device that took its place will inject this notification directly inside affected packets, in packets related to that slice, that service, in both directions, so that all the equipment traversed by the traffic, regardless of which segment, which operator they belong to, will be notified of this event and reduce their allocation accordingly. So if we compare MRECN to ECN, the main takeaways that we can derive are that first, they are not in competition because they have different purposes, namely ECN's purpose is to bypass packet loss in congestion avoidance, whereas MRECN's purpose is to bypass the control plane hierarchy to perform multi-resource allocation adjustments. And also where the recipients in ECN are end devices, the recipients in MRECN are the equipment traversed by the slice. But we can generalize it by the service, by the traffic. Then in this slide, we also have possible use of DSCP bits for the MRECN. This is just an illustrative example. In fact, it just looks nice because this way it is adjacent to ECN, but it's far from being set in stone. Actually, we will see later some further potential examples. But in this example, we envision 1 bit for to express the congestion experienced flag, 2 bits to encode which resource was impacted, 2 bits allow to represent 4 values, which can make sense in the network slicing use case, might not make sense in other use cases. And 3 bits are for the congestion severity to express the magnitude of the resource loss so that receiving devices can use that to perform their allocation adjustments. So speaking of allocation adjustments, to stick with the 5G network slicing principle of allocating tailored resources to based on requirements, we also allow for that flexibility in both how the congestion severity is encoded and how allocation adjustments are performed, meaning that each individual slice might have its own way of encoding severity. For example, one could use the last measured congestion severity as value to inject inside the packets. But maybe if the congestion varies rapidly over time, this could lead to frequent changes in the allocation adjustments, which may be not convenient depending on the service. So other solution could be the maximum to use instead the maximum congestion observed in the last period or the average, and so on and so forth. Whereas allocation adjustment means how much should receiving devices reduce their allocation based on the congestion severity. Again, assuming proportional dependency, one could use a proportional criterion, but maybe some resources might not have the same dependencies, or some services might require different strategies. So also this part could be an element of flexibility. This slide is just to mention that we have developed a prototype of FPGA-based switch that supports MRECN. In fact, it features a programmable packet scheduler that allows to assign per flow scheduling parameters, and also to adjust bandwidth allocation based on received MRECN. The RTL code for this FPGA prototype is not yet documented, but it can be provided on demand if someone is interested. And let me just wrap this presentation up with some final notes. As I mentioned, in this presentation we focused on network slicing, but actually it is just an example, and this idea could be employed in any multi-operator scenario where tailored resource allocation is performed. And actually, more in general, it can be employed in any scenario with a hierarchical multi-controller infrastructure. And then, as also we've already said, the use of the SCP is just for illustrative purposes, and in fact, it leaves some, at least some, the ones that are mentioned here, critical points, namely, we only have 2 bits for resource ID and 3 bits for congestion severity. But most importantly, what if there is more than one resource that is congested at the same time? What if we want to inject multiple notifications on the same packet? So some potential alternatives could be to use the MPLS header instead, similar to MPLS traffic engineering, or another dedicated header between layer 2 and 3, such as they do in INT, or also use IPv6 extension headers. So I am done with the presentation. Any comment, feedback is much appreciated.
And we have Ingemar first.
Yeah, I hope you hear me well. What I think I agree with Stuart that maybe the use of congestion could be a bit misleading, and I believe in some cases, I think it's in sometimes a disconnect between 3GPP and IETF what they really mean with congestion. In IETF, at least in the transport working group, we refer congestion as something that just do self-congestion on your own bearer or something like that. But here it looks more like you have some the load becomes so high so that you can't satisfy some service requirements on a higher level. So maybe need to find out another term on it then.
Yeah, I
another
agree with
one,
that.
I believe another one is a question if in-band signaling for this is the best alternative. Maybe for sometimes out-of-band signaling can be a better alternative, but I haven't read through this and probably need to read more to understand it fully. But thanks for the presentation anyways.
Thank you very much for the feedback.
Roland Bliss, KIT. Thanks for the presentation. I'm not sure. I mean, first one comment is indicating a congestion level is usually a good thing, because you just don't want to know that there is congestion, but you also want to know the severity. So this is quite useful. But I was wondering, first, is you said it's for any resource, but you are actually putting the value into an IP header. So I guess you're assuming that the IP packets are flowing through that resource that is congested, right?
Mm-hmm.
So it's not any resource, but a resource that is networked somehow. I guess. And the second thing on slide 10, you're sending the indication into both directions.
Yeah.
And I was wondering who takes action actually. Is it both ends, or do you need to coordinate, or is it the possibility that you overreact?
So the recipients for MRECN are not the endpoints. Actually, is the devices that compose the network physical infrastructure. So it is it's the congested device itself that injects this notification on both.
Yeah, I understand that, but who takes the action?
The other devices that are traversed by the same traffic, the packet that is injected with the notification.
Okay, maybe I have to read more about that.
Thank you. Did you ask something before that? Maybe I lost the first one. Thank you.
Hi, Altanai from Cisco Meraki. So I can't help thinking how this system can be weaponized, For example, because there's so many security implications of this in-band signaling, what if somebody tries to say, try to put high congestion where there is low congestion, so effectively reducing legitimate sources traffic to near zero, or even if not that, then these bits, the congestion status and everything, they expose the internals of a networking service provider, their resource IDs, so putting them in a very targetable position.
So I'm not sure I understood the question. You mean?
The question is, how do you make this safe against unfair usage?
That's a good point. We haven't thought of that. Definitely, we will now. But the idea is that you would use that in a context where different resource controllers are already supposed to collaborate. That doesn't solve the issue per se, but maybe it can be something that should be agreed upon among the different controllers before, of course, putting that in place.
Okay, so within the same service provider, because
essentially
the networks are zero trust these days. Everything is zero trust networks. So you're designing a system which is in a very trusted environment within a small network, right?
Yeah, I completely see your point. Yeah, it is a very, very valid point. It could be also, maybe it makes more sense to then employ it in a system where there is trust among the different resource controllers. Maybe they belong to the same organization, but hierarchically they are divided because they handle different segments.
Okay, All right, thank
Yeah.
you.
Thank you very much. This is a very, very interesting point.
Okay, Gary Fairhurst. Which packets actually carry these signals? Is it every packet that goes through the congested resource, or some of them, or?
In our implementation, all of them, yeah.
So every packet's marked with the same signal, yeah?
Every packet belonging to the flows or slice or service that is affected, yeah.
In both directions?
Yeah.
Okay, that seems like an interesting way of doing it, but I'm not sure whether it's better than an out of band one where you simply send a packet towards the destination. Have you thought about that option?
Come again?
Have you thought about just injecting an OEM packet into the stream and sending it that packet instead of trying to mark all the packets?
Might be an option. Why not?
And I have a little bit of a niggle against the use of DSCP for experiments because it kind of eradicates the use of DSCP for anything else. And EXP is the same field in MPLS, so you're kind of doing the same thing. So think about maybe which bits you want to use to carry that, and that might make it more deployable, perhaps.
Okay. I also mentioned at the end some potential alternatives.
Yep, extension header and
yeah.
Potentially an OEM shim. Yeah.
Yeah.
Thank you.
Thank you.
This is Rüdiger Geib, Deutsche Telekom. Yep, thank you. I am not an expert in 5G architectures. Question coming to my mind is that you assume identical path in up and downstream direction. Is that correct?
We didn't tackle that problem. It might not be the case. If that's not the case, I don't think it's a big issue for the purpose of the protocol, because other devices that receive the notification might relate in the correct destination, in the correct direction.
So they would return the information which they receive. They would reflect that.
If a packet is traversed by, if device is traversed by, I'm thinking about it right now, so maybe I might say something dumb. But if a device is traversed by a packet carrying a notification, then if on the other side, if it is non-symmetrical, eventually the notification will reach the one of the two ends. For example, could reach the in this example here, the data center where the service is hosted, and the server hosting the service in that case will propagate the injection, the notification itself. So it will eventually reach all the traverse device.
I didn't read your paper. Is there a discussion on the duration of these events? Because I mean, you have, say, one RTT until you figure out what's going on. Or
yeah. So as I was briefly saying here, there have been some papers that tackle the or try to estimate what would be a time for reallocate resources. Normally it would require at least with a centralized solution, so without the explicit notification, it would require at least the notification to reach the resource controller. Then it would require horizontal interoperator or intercontroller negotiations, later it would require recomputing the optimal allocation and then reconfiguring everything else. So of course, by injecting it directly on data plane traffic, it would accelerate that, even if it wouldn't result in an optimal reallocation, but in a coarse but more timely one.
Okay, thank you very much.
Thank you. Thank you.
All right. Going once, going twice. Thank you, everybody, for the discussion, and thank you, Mario, for presenting.
Thank you very much.
And so that brings us to our final presentation for today, which is going to be Kuhn giving us an update about FRS in Prague. Hang on. Oh.
Hello, everybody. A quick update, or yeah, can you hear me now? Maybe not so quick update on Alvarez and Prague. Work that we do on mainlining, also with Chayu Chang, who's mainly doing the mainlining, and then some further explorations on what can be done to improve Prague. So the first topic is this Linux mainlining. I already explained a bit in TSVWG. So for the ones who were not there, so it's a long process, it seems, with the chain of dependencies, and we have to chop it up in different parts. Lots of iterations for every part. So it is ongoing, bit of patience, but we're hope to reach this year at least, or next year somewhere, to have it finished. But in the meantime, of course, Chayu provides all those Linux versions which you can use and download. The source code is there. They are integrating all they have the plans to upstream patches already integrated, and we heard that people using these and they work pretty okay. Besides, we even can find problems in the specifications of Accurate TCN, so that's a good thing. They are running and used in the lab and in the field. I also explained a bit in TSVWG this possible network improvements, and I will shortly repeat them here because they might have impact on how Prague and Alvarez congestion controls should behave. So one of the important differentiations between classic and Prague Alvarez congestion controls is that the Prague requirements are actually made to remove all the reasons why packets need to be delayed in the network to control the rate. So you don't need to delay packets to and do an active queue management on them. You can immediately start marking them, and you can call that an active rate management if you actively directly manage the rate instead of let the scheduler determine the rates and let it block and create a queue and do active queue management. That's actually, yeah, if you don't need to build a queue, the scheduler is made to do this. Of course, there still need to be a scheduler and there still need to be a queue, but we hope that the schedulers are not blocking too much. That is possible at least. And I see, Stuart, you have a question.
Thanks. It's actually not a question. I wanted to give some clarification because this thing that you're talking about confused me for a long time until we talked about it. And I want to make sure it's not confusing other people in the room as well, because I think people come at this problem with different context, and that shapes how they imagine things are working. So you just talked about you don't have to delay packets. And I've had discussions with other people who were very confused about that, because in the context we were imagining, you obviously have to have a queue. If you have a gigabit Ethernet going into a Wi-Fi access point or going into a cable modem that physically can't send more than 35 megabits per second, then if you get a burst come in, which you will, because I want to make this real and not abstract and theoretical, Wi-Fi aggregates packets. So quite often you'll get a bunch of 50 packets as one Wi-Fi aggregate. And if that delivers 50 IP packets over the gigabit Ethernet link to the cable modem, you have virtually instantaneously, you got boom, 50 packets.
Yeah.
But the cable coax itself is dribbling them out at 35 megabits. You have to buffer them. Now, what you're talking about, this is, people can stop me if I'm saying the obvious, but Kuhn and I had a good conversation at the hackathon and it made it clear to me. What Kuhn is talking about is when you don't actually have a physical bottleneck where you physically cannot send more than 35 megabits per second. You have something like a fiber, and it can send a huge amount of data, but by contract, you haven't paid for that much. And you want to you want to throttle the traffic to the rate the customer's paid for, not because you can't carry more, but because you haven't agreed to carry more. And in that case, you want to do this ECN signaling to tell the sender, you've paid for 100 megabits, so you better do 100 megabits. But you don't actually have to queue up the packets because you're not dealing with a physical constraint. You can send them as fast as you like. You just want the sender to cooperate. And I think that is key for where you have to do buffering and where you can get away with not needing buffering and just doing the marking.
Yeah, but that's a very good example. For instance, where in the past you had to provide a shaper and a queue to control that rate to limit it, you can now do a marking policer that just marks those packets. But another point is also that you gave reasons to have a queue. But that's not a queue because you want to control the rate. That's a queue because the network needs a queue. So you still need a queue because the network needs a queue if you do aggregation, but that queue is there for aggregation and not to control the rate. You can avoid that you build a queue to control the rate by marking in a smart way so that the traffic can go through without being blocked for the next transmission opportunity or the next aggregation part. So that's the big difference. You still need queues because of the network needs queue, the protocols needs queue, but not for the rate control anymore.
Yeah. So hopefully this makes it clear to anybody else in the room who's confused like I was, because I've been hearing from other people that Kern is saying there should be no queues anywhere in any network devices.
No.
And I was saying, it doesn't sound like the kind of thing he would say. That doesn't make sense. So now we understand.
Yeah. Thanks.
So I also have a clarification question on the same topic, Chris Box, BT. So thanks, Stuart, for adding that part, because yeah, this is a difficult concept I find to grasp initially. In the way you've drawn these diagrams, are you saying that where you've got SRM arrow pointing to a thing on the wire, is that, so I'm interpreting that as that's where you're doing the CE marking, and then that goes into a queue. And we're hoping, in theory, that if everything's working correctly, the queue should be very short. Is that the correct way to interpret that?
Well, I just see, because I had to split the slides because it's I also have animations that there's missing something. So it's actually a bottleneck where you have a priority, let's say, for the alpha-REST traffic, but it's a latency priority, like in the dual pi square, a latency priority. So the ping traffic in the SRM example can go through, but it's not blocked by the pipe itself, because the blue ones are then the classic traffic, which needs to be queued if there is a bottleneck. But you can limit the pink one by you give it priority, but you limit its rate anyway with the marking, and potentially with dropping if it's unresponsive.
Okay, maybe I need to see the animations then, if that's possible.
Yeah, well,
there
is no animation here, but yeah, I see there was an error, but okay, it can be clarified. But think about it as a dual pi square, where you have a fixed mark policer actually that marks the packets. So a fixed rate policer that marks the packets.
Okay.
So it's not adaptive, and it's also not, well, it's actually like a dual pi square also gives feedback marks, just marks to the alpha-REST traffic without any AQM. It's actually a kind of active rate management, but then based on a policy which is it needs to get the same throughput as a classic. And how do you derive that? By the drop probability that you have to apply on the classic queue.
Yeah, that's normal.
So it's also doing active rate management, you could say. Yeah. If there is classic traffic, but if there is no classic traffic, then it gets its own queue and it gets its own active queue management. But there you could also, by giving some headroom, avoid that it even queues in the alpha-REST case, in the alpha-REST queue.
Yeah. Okay. Thank you.
And then the active rate management itself, like I said, can be based on different things than the policy, the drop probability in the classic queue. But anyway, all of this, the point here is important that that should be the next slide, that it has some impact on the congestion controls. So latencies can be very low and stay low even under maximum loads and maximum capacity that the network wants you to use. And then these PRAC requirements become very important, like this round trip time independence for lower than 25 milliseconds round trip times, because otherwise we mark, and if you have a throughput based on the round trip time, and this is like half a millisecond or few milliseconds, then you starve actually the traffic that comes from flows with 20 or 30 milliseconds. Also pacing below a minimum window of 2, because if your round trip or your BDP is less than 2, and especially if there are multiple flows going through a bottleneck, you're actually not limiting the rate. You're actually becoming how do you call it? Unresponsive. Yeah. So these things can be solved in the congestion control, so that the network doesn't need to make you a queue. And then maybe less important under these conditions are things like slow start overshoots. If there is enough headroom, it does not create latency under a rate managed queue. It just gives you an extra short rate overshoot, which should be then compensated because you get marks. And if it doesn't, then you will hit some other wall, which might be the scheduler or might be something that drops you. But of course, it still creates latency if only if it is the only flow on an alpha-REST step or slope active queue management where there is a queue. So the network can solve this. Not sure if we can solve the slow start or the speed up compared to how fast you go and how big the overshoot is on an active queue management. So again, it's a choose of who can solve what, and with alpha-REST, it's both parts can work together here. Okay, then for the PRAC congestion control, we have a module, behaves exactly the same as TCP PRAC congestion control, but it's kind of wrapped in an object that you can use in UDP-based applications. So it's a single CPP header and CPP file. It defines this PRAC congestion control object with minimal dependencies. It's I think it's using the STD, one STD for a monotonic time, which should be available on any C++ platform. It's a platform independent code and it can run on any C++ compiler. It allows also to evolve PRAC without impacting the API. So if you use this object, we try to keep this API stable. And of course, it can accept from anybody having ideas on how to improve PRAC to implement it there. Also, the API can still evolve if users think there are different alternatives how to measure round trip time. You might have different fields in your protocol, so we can add extra mechanisms to do these things. So it can do bidirectional sender and receiver mechanisms. So you need one in the sender and the receiver, and or optionally, but it helps if you you only need one instance on each side, whether you do unidirectional or bidirectional. And the good thing is also, and I will show you some examples, that you can directly control the application data generation and do a non-blocking delivery. There are some examples, and it is being integrated already in iPerf2 and also in NS3. It's integrated, but it's currently in a private Git from Cable Labs, but they will release it at some point.
Jonathan Lennox, so what does it fall back to if you're not in LFRS? Is it just cubic, or is it?
We'll come to that point.
Okay.
Currently it's Reno, but there are some ideas there to fall back. And fall back to cubic might be a good idea. Or we also plan to align it a bit with TCP Prague. This either cubic or a more let's say more big round trip time capable control. So stacks, like a stack, I see you have a socket API, you can use this proxy. You can include it in stacks if you want to. Typically a quick stack, I guess. The thing is that, okay, with a stack, it's of course having proc is a big optimization, but it's not yet the optimal, I would say. The fact is that the application has to give a bunch of data to the stack, and then the stack is actually controlling the rate with what the proxy gives you is a pacing rate and a window, and it's actually doing this locally here, doing its thing. It's draining your queue. You don't know in your application when the queue is drained, when it's empty. You need some flow control mechanism to control this. And is there a question related to this, Martin?
Go ahead and finish your slide.
No? Okay. So you need to do flow control and have to guess then also measure what's the rate, how fast are my frames drained and everything. And while this Prague congestion control has all this information, why not directly use it? And also if we do tests, like even measurement tests, like with certain tools, you actually measure and see mainly that queue, because that's really a queue, and under certain conditions when it's not managed, you see that latency. So for tools like iPerf2 and in NS3, we can really measure without any blocking the real end-to-end latency that an application would experience. So this is the more recommended use, that you have use these packet pacing rates and packet windows inside your application. Could be potentially some better API from a stack. That's also possible. And then also another thing is that Nix could also do marking instead of flow control, because it's all one loop. So if you do flow control, you have another system again. If the network interface is marking or any bottleneck is just marking, then you have with one mechanism the full end-to-end control of your application. And then applying it to video. Martin, you want to ask a question?
Yeah, I wanted to sort of feed off what Jonathan was asking. I'm a little confused. First of all, thank you for the
Your voice is very broken.
You're not coming through clearly, Martin. Yeah, try out.
Can you hear me now?
Yeah, much better.
Okay. Thank you for taking up the broad draft. I'm happy to see it move forward again.
Now it's bad again.
I think you need to use a headphone. Usually that's what fixes it for me.
Okay, I'll continue, maybe via the chat. Okay. Then yeah, with did I? Okay, maybe the order changed. So how do you apply this now to a video application, for instance? And so you have the full loop. You have a Prague congestion control object at one side and at the other side, and then you have a frame-based video stream. And just illustratively, okay, you have a certain Prague congestion control pacing rate. You have to pace your frames with that rate. If the pacing rate goes down, because of marks, you of course have many choices what to do. You can reduce the size horizontally, or then you can spread it over a longer time, and then you have an extra transmission time and more latency for your users, but it's within your let's say frames per second. Also, if there are hiccups in the network, you can stop sending or even encoding frames, sorry, and adapt potentially then also your internal frame per second. But by skipping it, you're already doing some kind of adaptive frames per second. Another, I have the impression okay. So another way that could be interesting, and a lot of people asked about burstiness and certain networks that prefer to have shorter bursts or longer bursts. So it is quite possible to try to pace them the same size that you would pace over a longer distance, over a shorter distance, over a shorter time, and experience whether you get more or less marks. If you get more or less marks, the network doesn't like you to bursts. So you better keep it paced over a longer time if you want to have the same frame sizes and quality. But on the other hand, the network might favor shorter bursts and do not mark burstiness. And that's also a way how the network can tell you your average rate might be good, but I like more bursts or less bursts. So if you see, I send the same average rate, and I just shrink my frames over a shorter time, and you don't get more marks, then that's good to find out whether the network wants more or less burstiness, while you preserve the right average rate. And like this, yeah, I thought I would have this slide first, but this explains a little bit. So if you have a video encoder, you can pace. You see, this is the output that the Prague congestion control module gives you, your pacing rate, your packet burst. That means how many packets you can send in one pace event. And then the packet size even, because we go down to 100 kilobits per second. And that means 150 bytes every 10 milliseconds still, because we want to have a certain interval in the interactivity at least. You also can then, of course, directly convert this pacing rate, whatever mechanism you want to use, into an encoding frame rate, or encoding rate or frame sizes. And then also with the window, you can block frames, not put them in the encoder, so you don't create the dependencies, and you can skip frames directly before you start encoding them.
Okay, let's try Martin's question again.
Oh, that was Martin's question.
Is this better?
Ah, yeah, this is better.
Okay, sorry about that. I'm not, it's not about the slide. I want to zoom out a little bit on the draft. First of all, thanks for moving the draft forward again. Like, I think this is an important document. I'm kind of confused about the positioning of it. It kind of, and when we refer to Prague congestion controls this as like a congestion control algorithm, but it feels like the draft is like a template that you apply to an underlying congestion control. And like, is that an accurate perception?
I didn't catch a question. Did you, Reese?
He says the draft is like it, or it looks like a template that you would apply to an underlying congestion control instead of being, I guess, a congestion control all of itself.
Like it's
Yeah,
Is
no,
that
okay.
accurate?
Yeah, the draft, I think we have to rework it a bit because it's now all more concrete. It still talks about research project. It's also here. I think we drive it to something which can be deployed, and so yeah, it
Well, I mean,
needs work.
what I find very difficult about it is, you know, like you can fall back to Cubic, you can fall back to Reno, which to me is two different congestion controls. So, like either this document can be, like I said, a template that you apply to congestion controls, and then I think you need some conditions on that. Like I think it only works if the loss-based congestion control. I don't know how this would work with delay-based, for instance.
Yeah.
And or like alternatively, we can kind of bite the bullet and have, it doesn't have to be two different documents. It could be like two different sections. Like this is like there's like Prog Cubic and there's Prog Reno, and they're like different in ways that are explained by those drafts, but these bits of logic are the same. Anyway, I think that make it much clearer to understand what we're talking about, because you know, when we just say Prog congestion control, we're obscuring a lot of differences in how things work. Thanks.
I get it. Like it's really, you know, like the difference is not in it is kind of template, if I were to say. Like it's not a new congestion. It's not, we're not rewriting any new algorithm. It's really how do you respond to this accurate CE marking? So nothing else changes. Like if you were to take cubic and you just add that to cubic, then it becomes Prague, right? Like I'm sure there's pacing concept and whatnot, and similar with BBR. You can apply the concept of CE marking and accurately responding to it to BBR, and that becomes a BBR with Alpha support in it.
Right. Okay. I mean, I think that's great. I think we should be a little clear about that in the document about what it's. I think we need to have. I think we need to change the way we talk about it to be clear on what the fallback behavior is when we discuss the performance of Prague, whatever. And thirdly, if you think it's straightforward to apply to BBR, I would love to see an example of that, because I'm.
Oh, there is a Linux that same Linux fork that we have on for L4S team. It has the BBR too in there.
Okay, that's great. That's great to hear.
Yeah.
Like I'm not 100% sure if I can look at Linux code and then just like copy it. Like some text that talks about the, you know, how delay-based congestion responses, and Neil's getting in the queue, so like he could probably answer my questions, but some sort of text about delay-based responses and how they interact with this would be wonderful.
Yeah, that's a good point, because that's one of the questions also I mentioned. Should we integrate here a delay-based? And even what is the other congestion control? I think by exporting all those windows and things, you can easily combine it with just another instance which is delay-based, which might use the same input, but then calculates its own window at its own pacing rate, and then you take the minimum of both typically. So that's how I think it can be combined, and you can combine different congestion controls in your application by just looking, okay, if I don't get ECN marks, I only see loss, then I switch to my loss-based one, which kind of then, when the last congestion event was loss. So I synchronize the windows or the pacing rates based on this in the other congestion controls. So something like that. Yeah.
Okay, lovely. Thank you. I look forward to the next version of the draft and you know, implementing off of it. Appreciate it.
And I think it would be good that people start using this and can give feedback how they did it and how it can work and how these APIs could work together. But okay, the congestion control here, we implemented it here in user space, so it's very easy for people to use it. It's exactly the same what we do in the TCP, and we will upstream. So yeah, okay. So it will help also to clarify those things and put it in the draft afterwards. I see, Gori, you have also a question.
If Neil's on the same topic, he can follow up first.
Well, I don't know what topic you're on, so go ahead.
Okay, I was on the previous slide where we were doing the video stuff, and my head blew up. So I was take a moment to try and work out what we were achieving here. I mean, this seems to be looking at optimizing the congestion controller to find a rate with some sort of ABR or adaptive video codec with a notion of what we needed in the video stream. I mean, do we need to put all these things together at the same time? Is it?
Well, that's the point. Is UDP proc object doesn't know anything about how you're using it. It just gives you a pacing rate, and this is an example. You can use it in this way for video, because there was a lot of discussion, and that's actually the separation. If you want to use it in a normal stack, you can use it immediately in a quick, because there it's only where is it? Yeah, like in here, it just gives you the window how you have to pace the packets which come from your application, which has flow control and maybe schedulers and whatever inside. So this proc CC is just a plug and play box that you can include in your application, and how you want to use it. These are just examples, and it's in line with the TCP proc. So you can in Linux at least, it's easy to use then also in applications and be immediately compatible with the proc, TCP proc.
But is there anything in the video application which actually needs TCP proc, or does it just need an optimized pipe over which it can send?
No, the application, the video encoder needs to adapt. That's the main important thing, and what we do is we set the video encoder in low latency configuration with constant bitrate, and we change the constant bitrate every frame.
Yeah, but why are you using that sort of, why are you actually using a video codec that's an adaptive video codec that adapts to the capacity of the pipe? I mean,
yeah, that's how it's done today, but that's not so efficient, because you have a pipe, and we know internally in the proc congestion control what's the capacity of the pipe. And actually what we do is we let you fill a buffer, you queue delay frames, and we let you guess what is the frame rate, right?
Yeah. Well, the video codec determines the frame rate, yes, depending on what the experience.
Sorry, the frame rate or the target rate, the bit rate of your video encoder.
So the ABR algorithm.
The ABR, yes. The bit rate, yeah.
Okay, maybe my head's just done. I'll talk again later.
Yeah, so it's just how you have to feed the encoder with a bit rate. The encoder itself knows nothing about the bit pipe, right? So you have to have a mechanism, and today it's done by flow controlling, keeping a buffer very small in the stack, and then estimating or measuring how long it takes to send the frame, and then you have already another frame back to back, and if there is delay in one frame, you just pile up and the others delay. While in here you can make it really low latency, and that's how most real-time video cloud gaming and also conferencing works. You send a frame, and you want it to arrive in time and not delay the next frame potentially.
Just a quick comment, Gori. I agree with you. I think we need to discuss this more. When I looked at these slides, I think I had the same reservations that you. There are some assumptions here that I think I don't agree with. That if you use TCP or QUIC, that means you have an extra queue that delays the data even more. And to me, that's a false assumption. Sending data over QUIC, there's no reason it has any more delay than sending raw UDP packets, except it does it better and more competently.
Yeah, of course. It's not the quick protocol itself, but it's let's say the socket API that is available that doesn't inform at which rate it needs to pace your packets.
Like I said, I think we need to explore this more, because I don't know any quick implementation that uses the sockets API.
Okay,
that's very archaic API.
Yeah. Okay.
Okay, let's have Neil first. Next, maybe.
Neil.
He's been in the queue.
Yeah. Hi. Just wanted to say that in response to some of the remarks a few minutes ago about prog being kind of just the obvious way to respond to accurate ECN, I just wanted to mention that I think it's important to note that there's more than one potential way to respond to accurate ECN. And in particular, you can have a different response function in response to the ECN marks and a different mathematical function that maps between an ECN mark rate and ascending rate. And so in particular, the ECN response that's in the BBR version 2 or BBR version 3 code that folks might be thinking of, that has a different response to ECN than PROG does. And so it would not interoperate well with PROG over the public internet. And so I think in the long run, we want a version of BBR that does interoperate with PROG. And that would be future work. And I think that kind of links into what Martin was saying, was that there's future work to be done there, because it's not trivial to make a BBR that interoperates with PROG. And that brings me to another thought, which would be that it might be nice to have in the draft some appendix or something that has guidelines for how congestion control implementers could take their existing congestion control and make it PROG compliant by essentially sort of running the PROG algorithm on the side, and then making sure that their final congestion window and pacing rate were kind of the minimum of what their existing congestion control would send at and what PROG would send at, just to give people a template maybe for how to apply the PROG ideas to their existing congestion control. And then one more thought would be, I like your discussion about using ECN for active rate management. And I just wanted to mention, for folks who haven't seen it, there's an interesting SIGCOMM 2005 paper that is kind of in this vein, where they basically came up with a congestion control algorithm that is using utilization as a signal rather than queuing. And in fact, it uses the two ECN bits for signaling, though in a way that's slightly different than L4S, but it's in the same vein. But I thought that might be interesting for folks, because it gives you a sort of fully worked out congestion control algorithm that uses utilization as a signal, and therefore, if everything's working well, it doesn't build queues, kind of like Kun was talking about. Thanks.
Yeah. And related to
Can
your
I
first
just,
remark,
Can I just ask a follow-up question to Neil? So you said the PROG BBR v2 where L4S or accurate ECN response was integrated. Is that the one you're saying does not interop well with PROG?
Yeah, exactly. Sorry. Yeah, it's a different response, so it's not going to interact well. Yeah.
So do you plan to, like, I don't know, in BBR v3 or something, do you plan to have something added for L4S support, or like responding to accurate ECN marking?
Yes, but right now it's not an effort that's staffed, and I've got a fair number of other things on my plate. But it's definitely something that I support, and if there are other people out there that are interested in working on it, I'd be happy to collaborate on it. Yeah.
Okay, I'm just asking. Yeah, I was asking because I want to know, like, what we have in that open source fork for BBR v2. That should people use it or not? If your recommendation is that is probably not that folks should use.
Right.
I'm not too sure.
If they intend for it to be something that would be coexisting with PROG or with PROG, then they probably shouldn't use it for that. So that BBR version 2 or BBR version 3 ECN response was sort of developed independently and was intended for data center environments and not for coexisting with PROG, because PROG was sort of developed in parallel and hadn't sort of fully fleshed itself out during that development timeframe.
Okay, sounds good. Thank you.
Related to your first point, I think to have it well described in the draft, the goal of this C++ code is to have a well-structured code. So it's even more, let's say, formal than how I would be able to describe it in a draft anyway. So it's off-the-shelf usable. So you can try and use it and integrate it in your application or combine it with your delay-based congestion control or potentially other congestion control. So that's the way to, and also have an easy platform, because the kernel code is very complex and a lot of dependencies spread all over. Here we have clean events, a few ones that have all the steps that are being done, so you can easily read it, understand it. Hopefully we'll have to use the draft to explain all the steps maybe, but at least it's the beginning. It's well structured, it's to the point, and yeah, easy use. So if you look for an implementation that is the TCP proc, and we will see, we have been experimenting a bit with other stuff, which is not yet in TCP proc, but we hope we can align this. As you saw, we still have some time before TCP proc will be upstreamed, so there are still things that we explore here now with this UDP proc CC module.
Thanks. Shall we hear Ingemar next before we go on with the slides?
Yeah, I have a little bit of a comment around this buffering on the sending side. I'll give you one example here. When I was working with Scream, and one conclusion is that you probably need to have some kind of sender buffer. And the one reason is that the video coders, for instance, can be a bit sluggish, and it can take a couple of 100 milliseconds in the worst case before it has adjusted to new target bitrate. And that is perhaps if you have static channels, then it's not that much of an issue. But it's going to have a dynamic change in channels, like in 5G access, and you need to have that to avoid bloating your own queue and getting a lot of excess LFRS marking because of that.
So
that is my impression.
Yeah, but it depends on your encoder, of course. You really have to encode it in low latency without iframes, with a CBR, so a target per frame that you can set. So and this is what you can use, and there can be some jitter on the frame sizes, but of course if it's iframes every half a second, which are 10 times too big, then that's the point of work.
So, for instance, one example is a VP8 encoder that was used in the WebRTC experiment, and that appears to be a bit sluggish. On the other end of the spectrum is NVENC, that is, it switches from one frame to another, so it's real fast, and so there are a lot of variations to it, and even with a gradual decoding refresh, and you still have it. So.
Yeah. Okay. Yeah, it depends, and also encoders will need to adapt to doing this. I guess if you really have real-time encoders, like I guess NVIDIA uses for cloud gaming, they are optimized for that.
Yeah, it's a matter of optimization, perhaps. Thanks.
Yep. Thank you.
Neil, is that a current hand? Otherwise, we have Stuart.
No, sorry, that was Dale. Go ahead.
I just wanted to follow up on that previous comment, because I think that is at the heart of some of this trouble people having understanding. It comes again from having different assumptions. The video encoding that I have worked with is one frame at a time. That you call the API and you say, give me a frame now, one frame, and compressed at this quality level, and that's it. And then you take that frame, you send it at whatever rate you decide that is appropriate to send it, with pacing and congestion control. Maybe you're limited by the first hop link if it's Wi-Fi, whatever it is. When you're done sending that frame, you go back to the video source and you say, okay, I'm ready, give me another one now. And the if the grabbing the frame and compressing it takes a certain number of milliseconds, then you want to pre-prime that process so that when you think that you're about 8 milliseconds away from being done sending your packets, you trigger the process so that ideally it is ready with the frame at the exact moment that you're out of data and you're ready to send the next one and there's zero backlog. You are describing a different programming model where the video encoder is kind of a free running process like a freight train, and you say, go, start giving me 30 frames a second, and it's going data, data, data. And then you go, whoa, slow down, that's too much, I can't handle it. And it takes a while to put the brakes on. When you're talking about it being sluggish, it doesn't adapt very quickly. And then you can get 5, 10, 15 frames behind before the brakes come into effect. And and then if you overshoot the other way, the pipe runs dry and you're not sending data.
Yeah.
What kind of hardware you have, what kind of camera, what kind of compression software you have, I think has a big impact on how you think about this whole problem. So I'm not expressing an opinion either way there. I'm just saying I see why different people look at the same thing and come to different conclusions.
Yeah. And it depends what are the capabilities. If it's a hardware encoder that indeed gives you those frames and you have to take them as they come, then you need to create a lot of headroom in your application already. So it means you probably will be bursting them pretty fast. Where is it? Is in here?
There are different video
and then
pipelines. So some have to work at a particular frame rate, and others can handle the interval between every 2 frames is completely different. It's like this one's 7 milliseconds, that one's 12, this one's 3, and just it's completely variable frame intervals. But as you say, some of the hardware encoders, like if you're doing an MPEG-2 stream, you don't have the luxury, I don't think, of having variable frame timing. It has to be on a fixed cadence.
Well, you can decode them and then re-encode them, but that takes time as well, and that's what we did as well. So, but okay. I guess that you want to have low latency hardware for low latency applications as well. So it's the whole ecosystem that needs to adapt a bit. And
this is why for low latency, I'm an advocate of what I described first, which is the just-in-time data generation. At the moment you're ready for data, then you tickle the camera, the encoder, the pipeline, the whole system, and you say, I want 1 frame. It's like that Hunt for Red October, 1 ping now. Just, I don't want a stream of frames. I want 1, and I'll let you know when I'm ready for the next one. And you need a very agile system that can actually deliver a frame on demand when it's asked for it in an instant. Because if you've got a pipeline that takes a while to get up to speed, you can't ask it for 1 frame at a time. But ideally, if you can have a frame when you want one and not when you don't want one, that's the best.
We control it from the frame source, which is raw video, and then we put the frame in a waiting block there. You see,
but when
there
you
in the
say
beginning.
the frame source is raw video, there's even assumptions.
It's a camera
there.
or
right, but a camera is an image sensor, and you say to it, "Give me a frame now."
If that's possible, then that's great.
Right. I mean, my camera takes a picture when I press the button. It's not.
Yeah, but it's a video camera which works in frames. I don't know whether you can trigger them.
But it comes down to can you choose when you want the frames, or do you have to start a free running process?
We assume
30 or 60 or 240 frames a second.
If you can, of course, then it's great. Then you immediately can trigger when your window comes in, you can trigger and deliver the frame. But if we assume the frames come at a certain frame rate,
if you
and then you have to override the previous frame if you don't want to lose the frame once it's encoded. So you have to block it there, and if it's overridden by the next frame, then you can send it and you take that fresh frame and not the old frame.
Yeah, if you've got a camera hardware that just generates 240 frames a second, then I would just ignore the frames I don't want and cherry pick the ones I do out of that 240 FPS stream.
Only the latest fresh frame you take in. So that's the gray box there, storing only the most recent frame. And when your window allows it, your packets in flight, you can, frames in flight in this case, you can take the one which is most fresh. Okay, let's speed up a bit, I guess. How much time do I still have?
26 minutes.
26, okay.
20 minutes.
Yeah, sorry. So also you can make it very complex, and also I would say keep on using Classic if it doesn't need low latency. If you have a big blob, Classic is great to fill the pipes and to give the networks also a buffer to process data when the alpha-res streams suddenly stop, or you know, alpha-res is a little bit more has more inertia and slower catching up in filling the pipe. Either you fill the pipe and you have a buffer which is big enough, or you have an empty buffer and then you cannot fill the gaps if there are variations. So using both is I think a good strategy for applications. Then related to this Prac object, it's just a single object, Prac CC you instantiate with default parameters, and then you we made a certain message structure which has common for up and downstream timestamps and echo timestamps. Then for the ACKs, you have a counter that counts the packets received, the packets with the CE, and the packets which were lost. It's just incrementing counters. Or lost can even be decremented if there is out of order. Then there is also an indication that there is an error in alpha-res. To avoid that, you have to have all the code points. Maybe it's good enough if you only use ECT1 in your application at the other side. Only have to check whether it sees ECT 0 or non-ECT, and then it sets the bit as an error. And then for sending data in the sending direction, you have a sequence number, which is always added. And then whenever the receiver, which receives the data, needs to send the ACK receives data packets, you get an event, or in a loop, you call the Prac congestion control. The packet received is in general to handle the timestamps. And then the second call is when you receive a sequence number, you call it with this receive ECN, which is the ECN that you extracted from the IP header. You have to give it, and then you give the sequence number of the message data, and that's it. And then when you want to send a packet, you call the get time information on the packets, whether it's an ACK or a data packet is the same. And then you can ask the acknowledgement info from the object, because it keeps track of the packets received, the packet CE, the packets lost, and whether there was a wrong received ECN seen. Same for if you receive an ACK, that's on the sender side. You have to be steered by the ACKs, and when you receive an ACK, it also has a timestamp, so you call the packet received to measure the round trip time. You call the ACK received, which fills in the feedback from the ACK packet into the Prac congestion control, and you can get out the in-flight, and it also informs you when there was an alpha-res error from the other side detected, so it stops you offering you these to use the ECT1 field. And then you have to call on pace timeout, for instance. It depends a little bit how you want to do the pacing. We did it with a timeout and in a single thread, but there are multiple possibilities. So you kind of, when you receive an ACK, you have to make sure you trigger or check whether you can send now a packet if your window was blocking. So you get the first thing you do if you want to send a packet is to get the congestion control info, which gives you the pacing rates, the packet window, the packet burst, so how many packets back to back you can send, and the packet size. And then you just do a loop. As long as your packets in flight is smaller than the packet window, your in burst is smaller than the packet burst that you have to send, and as long as your next send, which you can manage when with the pacing rate, is smaller than now, then you can start sending packets. So again, get time info for a data packet, fill your data with the, your packet with the payload and fill in a sequence number, and then that's it. And then at the end, you calculate if you get blocked due to some of these things, or either the window or whatever. There are different conditions, so you can schedule events if necessary. There is also a retransmission timeout. We have a reset congestion control info, which goes to initial window of 1 and slow start, well, very slow start. Yeah, then you have to call again this on pace timeout, for instance. Okay. So the PROC features in general, which apply to TCP PROC and PROC congestion control. We have, based on the marking, a round trip time independent downscaling of the increase to make it round trip time independent under 25 milliseconds. We have this minimum window and minimum rate scaling down to 100 kilobits per second, and we can pace below the minimum window. And then pacing is in bursts of 250 microseconds. These are probably known already, just PROC requirements. What we have added is for these really low rates also a switch whether we update the window or the rate. I can give some explanation. We added also a sub round trip time plus and minus 3% pacing. I'll explain as well. We did this PRR like reduction in PROC-CC, which was already in TCP PROC. And we are testing now further whether we can have this multiplicative increase after a certain amount of additive increase, so that you can speed up when you don't get a mark when you expect a mark. And then we actually use that mechanism also to make the loss-based round trip time independence for the bigger round trip times. So it's similar like cubic, but different. And we are evaluating what can be the best, this mechanism or cubic. And then not yet decided, how do we want to build in a delay-based congestion control in this, or do we expect that people use their own delay-based? I guess it's a special art building delay-based congestion control. So I don't know whether we at least want to risk us if somebody has an easy one that we can implement and which can be overwritten by others, that could be done. But I think it can be better combined and be independent. So this rate or window update is we did because when we do these really small round trip times, actually the jitter, a small jitter on a small round trip time can become relatively a very high jitter compared to your base round trip time. If you have already 20 milliseconds and 1 millisecond jitter, that's not a problem. But if you have half a millisecond round trip time or even 1 or 2 and you have 10 milliseconds jitter, then this becomes a factor 10 or up to 100 we saw under certain conditions. And if you then update the window gradually and your smoothed round trip time varies with a factor of 10 to 100, then your pacing rate will also vary with a very high variation, and that doesn't work that well. So in that case, it's better to update the pacing rate and derive the fractional window from the round trip time that you get, the smoothed round trip time. In case it would be bigger than 2 packets, then you can increase the real window. And this switch is based on whether your smoothed round trip time is below 2 milliseconds. We configured this now, but it can be changed based on experience, or below a certain pacing interval, below the pacing interval, the active pacing interval. So if you pace every 10 milliseconds, then you don't want to measure jitter, because those packets, when they get serialized, the jitter can be 10 milliseconds. So that's the reason. And then when we do the switch, it's also important to keep one of the 2 stable, and we take the rate as a stable, the pacing rate as a stable switching point. So that works pretty good. And if you have a queue building, then it becomes bigger than 2 milliseconds, then the window, it becomes a limiting factor. If not, then you have a stabilized throughput for those low rates and low round trip times. Then also the sub RTT pacing with plus and minus 3%. So it's actually to kind of avoid this on-off marking and that you have on a step AQM. It improves a bit. This on-off marking is not so good for the dual pi square because it influences the round trip time fairness. On the other hand, it mostly happens in simulators or on very stable link, and just to avoid it, that people start complaining about it, we made this every first half of the round trip time, we pace 3% faster, and every second half of the round trip time, 3% less, and then you get rid of the on-off marking, and you get a very stable rate and a very good round trip time independence between flows. If it's necessary, if it's a stable link, because there is already a lot of fluctuation on real networks. Then the other thing we've been experimenting with, and we want to do some further testing, is so can we in speed increase the increase from Reno, or do we have to switch to cubic? So the idea was, can't we, after a certain moment, start increasing with 1 millisecond per second? It's the threshold is 1 millisecond. Well, we can. So you saw before it is about 3 seconds. If we increment 1 packet per round trip time and we change the bit rate from, or the capacity of the link from 40 megabit to 100 megabit, you see the latency is nicely around this 1 millisecond. You see the marking probability there as well. So if we do this, we can calculate when do we expect in worst case another mark. If you don't get this mark, can't we then assume that there is more capacity and do this 1 millisecond per round trip time increase? And that works, and it gives a big improvement. So you catch within 1 second the whole capacity instead of, or less than 1 second instead of 3 seconds. And the current algorithm is quite simple. It's based on the theoretical model. What's the worst case of this on-off marking? And it seems to be a simple equation, is that you have to count the round trip times as the pacing rate divided by 15.36 megabits per second plus 7. And then that's the first thing further to be further evaluated, whether this holds under all cases, but it's definitely a good improvement. So the main goal was to get getting faster new capacity, and we found a few bonuses with that. The faster convergence, it helps to faster converge actually, because the low rates, they go faster in this multiplicative increase, and before the big rate will do that, because the rate divided by 15 megabit is more round trip times before it starts. So you get a faster convergence. It seems not always to work, so we want to see what further can be done about it, but it's already good that it would work under the different conditions. And we also feel that it may be deactivated by these plus minus 3 variations, because then the chances that we get an interval where we don't have marks which meet that is smaller, because we get this continuous small throughput. So it's a bit maybe thinking we have to deactivate it under certain conditions, this plus minus 3%, to be further looked at. But the code is there, it's working, it doesn't do any harm. Also, the downside is that during that conversion, actually, this 1 millisecond is an overshoot over the threshold of 1 millisecond. So you see often peaks of 2 milliseconds, if that is a problem. But that's not a problem when you do this static rate management or active rate management. It's only when you have an active queue management. And then can we replace cubic with something similar with this 1 millisecond increase? And then there the same question is, one would, let's say, a 25 milliseconds flow would expect a mark or a loss in this case, because it's loss-based response. If we get a loss, we use the equation below to calculate after how many round trip times, the bigger round trip times, we will start in this new growth. And you see here a flow of 25 milliseconds and 50 milliseconds. You see they get about the same duty cycle. So that's a good indication that they will get the same throughput. Okay, so it's all there. What we also did is we made a virtual, the now function virtual, because you have to provide your own virtual, your own now timestamp, which we use a standard monotonic clock in C++. But if you have a simulator or another clock you want to use, you can override it. This PRR-like reduction was also now in UDP Prague. It was already for a long time in TCP Prague. And things to do is maybe this window growth limit. If it's up limited, we have to think about it, but this is only for UDP Prague, of course. And then maybe we were thinking to create also an API that does the conversions to the video frame rates and so on, but or the frames in flight, but maybe that's not necessary. And then, yeah, the delay-based policies. I think we all discussed this up front. That's it from my side. Sorry for the long presentation. I hope everybody is still awake.
I appreciated the deep dive. I think we touched on many important points for Prague. Anybody have any more thoughts right now? We do have 8 minutes left in the session.
Roland Bliss, KIT, thanks for all the work. I mean, you mentioned that you looked at the lower bandwidth limits. What about higher bandwidth? So did you test with 10 gigabit per second, 100? What, I mean.
Yeah, I don't have all the results, but we are here in the interop. If you're interested, can have a look. But it is improving also. So, and based on calculations, it can compete with cubic and even be out-compete cubic. So, and only create 1 millisecond.
Okay, thanks.
So if it is DOS, then it's a very simple implementation instead of cubic, I would say. And a good advantage, but.
Yeah, my background was that you have all these jitter and timer issues that gets harder if your speed gets higher. So especially at 100 gig or even at 10 gig, then you get jitter from operating systems and stuff. So I was wondering whether some of the variables that you are now using or setting whether they are appropriate for scaling towards higher speeds. That was my concern there.
Yeah, we did. Mainly our variables are quite big, so bigger than in the TCP stack. But we had an issue with the increment that we calculate, that it was wrapping around at a certain moment, and we saw these things. But these things are fixed, and indeed, depending on the rate and it's one of the problems. And also, if you implement your own congestion control, you will find out that all these variables need to be big enough, and it's all integer calculations, at least here. So it's a hard point to check all the conditions that they never wrap around or get limited. So that's why it's also easier to take one off the shelf. And you can adapt if you're not happy. And of course, contribute if you find better solutions.
I see we have Stuart again.
It seems like we're probably finished, so I just want to end again by thanking Koen for all of this amazing work he's done. It might seem like we disagree on some little details, but broadly speaking,
Good discussion is good.
yeah, we have good discussions. I'm really impressed by clearly the amount of work you've done on this and the depth of the study, and I'm looking forward to seeing this widely deployed on the internet because it's going to be a game changer. Thank you.
That's why we do this. Okay, thank you.
Thank you. Excited to see this work coming along. And as we don't have more thoughts on this right now, I look forward to seeing the updated draft that Kuhn mentioned and to continuing the discussion in future sessions. So with that, we're going to wrap up 5 minutes early. Thanks everybody for your participation. Thanks, Vidi, for your co-chairing remotely.